So, ladies and gentlemen, I'm the head of a DAMTP, which is the Department of Applied Mathematics and Theoretical Physics, and it's my great pleasure to welcome you here to the 6th Andrew Chamblin Memorial Lecture. The first 5 lectures have been given by Stephen Hawking, Roger Penrose, Paul Davis, Michel Mayor and Brian Green, and we're very pleased that this year for the 6th lecture we've got him, Al-Khalili. So before I introduce Professor Al-Khalili, I'd just like to say a few words about Andrew Chamblin, in whose memory this lecture series has been established. So Andrew was born in Lubbock in Texas, and he attended Rice University before coming to the UK. He first went to Oxford, where he studied twistor theory and general relativity with Roger Penrose, and then he moved to Cambridge, to St John's College, where he worked as a PhD student with my colleagues Gary Gibbons and Stephen Hawking in DAMTP. Over time, his interest turned from twistors and general relativity to quantum gravity and M-theory, and over his career he made several striking research contributions, publishing over 50 papers and delivering many talks and lectures. So after he finished his PhD, he became Draper's research fellow at Pembroke College, and then he moved on to other postdoc fellowships before going to University of Louisville in Kentucky, where he was an assistant professor, and it was there where he unexpectedly died at the age of 36. So Andrew's many friends and collaborators in DAMTP and Cambridge and across the world have established a fund to support this series of lectures which perpetuate his memory and also promote the broad area of science in which he was interested. Sufficient money has been raised to essentially run this series of lectures in perpetuity, and we in DAMTP are very pleased to take responsibility for it, and it's regarding it as one of our important annual lectures. And so it's a great pleasure today to welcome many of those who've helped set up this fund and indeed given to it. Andrew's parents often attend these lectures. Unfortunately, they can't be here today, but they donated this striking bust of Andrew, which is on display in DAMTP. So each year this lecture is a chance to remember him. So now I'd like to move on to introduce our lecturer, Professor Jim Al-Khalili. Jim is Professor of Theoretical Physics and Professor of Public Engagement and Science at the University of Surrey. His research is in theoretical nuclear physics, particularly as applied to exotic nuclei produced by radioactive beam facilities, and his interests also extend to nuclear astrophysics and quantum effects in biological systems. But he's also well known as a communicator of science. He's written several popular science books, presented several TV programs on scientific topics, most recently a Horizon special on the early results from the LHC. He's a frequent presenter or guest on the radio, and indeed over the last few months he's had a regular Radio 4 slot. It's a Radio 4 slot at 9 o'clock on Tuesday, which is a prestigious slot. Called the Life Scientific, and there are still a few more programs. Yes. In these programs he interviews leading scientists about their life and work. And so his success in communication science has been acknowledged by the award of the 2007 Michael Faraday Prize of the Royal Society and the 2011 Kelvin Medal of the Institute of Physics. So very pleased to have Jim here today at our lecture. His title is On the Shoulders of Eastern Giants, the Forgotten Contribution of Medieval Physicists. So please welcome me please join me in welcoming Jim Al-Khalili.
Thank you very much, Peter. Well, good evening, ladies and gentlemen, and apologies again for making you wait. I don't normally insist on such a grand entrance. I was always going to be tight. I was up in Birmingham this morning and got the train which would have got me here about 3:45, but there was a fatality on the line, which meant that everything was held up for an hour and a half. And you know, I always make sure I never complain about these things. However, you know, it puts life into perspective. I think I've kept you waiting for a few minutes, but some poor soul has had to. Anyway, so the lecture this evening. It's based on a book I wrote recently that came out hardback and came out in paperback, and it's really on the history of science. And in writing the book, actually for a period of about 2 years, my research wasn't into theoretical physics; it was into history, and I found that very refreshing and different. You know, history is not like science. In science, you know, you can't have different opinions, either right or wrong. It's pretty much in history you can say what you like. Provided you go to primary sources, you know, you can say, well, so and so thinks this. I think that's a more important aspect, and so on. So I found it very, very refreshing. So what I want to focus on this evening, and it's a great honour actually to give the Andrew Chamblin lecture, and particularly after such a prestigious array of physicists performing. I want to focus on the physics rather than general science, but essentially what I'm talking about is a golden age of science that is pretty much forgotten in history. We, particularly in the West, we tend to think of the ancient Greeks, very clever chaps and deep thinkers, and gave us geometry and so many other disciplines. And then Western Europe goes into the Dark Ages with the fall of Rome, and we assume nothing happened in science until the Renaissance and the scientific revolution, Copernicus and Vesalius and so on. But of course, just because Western Europe is in the Dark Ages doesn't mean the rest of the world is. And over this period of about 1,000 years, from about the 4th century AD to the 14th, 15th century, China had a great civilization, India had a great civilization, and indeed the Islamic Empire nurtured science and learning and scholarship. So my book was called Pathfinders. It was originally going to be called The House of Wisdom, and I'll say something about that famous academy in a moment. It was going to be called The House of Wisdom, and then my publishers, Penguin Press, realized that there was another book with the same title on the same subject published in America. And initially they were quite bullish about it. They said, no, look, we'll let them worry about, you know, they have the same title as us. You know, we'll be fine. And then just before publication they got cold feet and decided they'd change the title to Pathfinders. It's a quote which I thought was attributed to a medieval scholar from North Africa, Al-Khalili, who's regarded as now historians of science and of social science see him as the father of social science, the father of economic theory and so on. And he wrote a very famous book on the political history and political theory. But I couldn't find the quote by him, and it turns out, in fact, it was a quote about him by an author, Nathaniel Schmidt. The quote is this: "He who finds a new path is a pathfinder, even if the trail has to be found again by others. And he who walks far ahead of his contemporaries is a leader, even though centuries pass before he's recognized as such." And Al-Khalili really fits that description, in the sense that it's only in recent years that scholars have recognized his contribution to scholarship. And in fact, it's really a title that I think fits well with many of the scholars, some of whom I'm going to tell you about in this lecture, because we don't know much about this period and these scholars. Even in the Islamic world, in the Arab world in particular, their names are known, but only known as figures in history, not how they fit into the pantheon of science and the development of science. So we in the West would have heard of maybe names like Avicenna and Averroes, but not really knowing what their contribution was, other than being great thinkers and great philosophers who may have influenced later philosophers. Well, I should also say this is the golden age of Arabic science. Why do I call it Arabic science? Might it not be more appropriate to call it Islamic science? And indeed, a lot of people have commented about this, why do you call it that? Well, firstly, I think we should never label this period, or any period, by the religion of those who follow it. I mean, after all, we wouldn't talk about Christian science, or if we do, we need something very, very different. I'm not going there. Likewise, Jewish science was a name used by the Nazis in the 30s to denigrate and belittle the work of people like Einstein, suggesting that it wasn't as good a quality of scholarship as good proper Aryan science. And so Islamic science isn't a name I would like, and it's not something that I have chosen to do. I mean, these historians of science avoid that term as well. And in any case, this is a period, a golden age, when many religions or scholars from many different faiths were coming together. In particular, in Baghdad, the new capital of the empire in this period, there were many Jewish and Christian and Zoroastrian and Sabian and scholars who all worked together side by side. So, what is this period? Oh, and of course, note, it's Arabic science, not Arab science. If I were to list my top 10 scholars of this period, I suspect more than half of them will be Persian, not Arab. The point is, Arabic was the language of science. It was the language that all the texts were written in during this period. It was the language of the Quran, and that being the official, therefore, language of the Islamic Empire. The period begins round about the early 9th century AD and carries on for several centuries. It begins with a translation movement, translating texts mainly from Greek into Arabic, but also from Sanskrit and from Syriac and many other languages that had also probably been influenced by the Greeks. So the important texts were books by Euclid's book on geometry, the elements, or Ptolemy's book on astronomy, or the works of Aristotle and Plato, or Galen, the physician. Many of these books were known about when the Islamic Empire expanded and overran the Byzantine Empire and the Sasanian Persian Empire, and a lot of these texts were inherited and translated into Arabic. And for a period of about 2 centuries, some books were translated more than once into Arabic as the scholars learnt more about the subject and understood it and were able to produce better translations. Why am I interested in the subject? Why did I become interested? Well, I was born in Baghdad. Although my mother's English, my father's from Iraq, and it's only in recent years that I've sort of felt some sort of a cultural tug towards my heritage. So my interest is purely intellectual, not spiritual. I'm not religious, and therefore I'm very careful not to sort of over-egg things, not to try and suggest that this was the most wonderful period in the history of science and the greatest scholars lived in this period. I'm always reminded of the sitcom that was on a few years ago, Goodness Gracious Me, the Asian family, the elderly Indian gentleman who went around insisting that everything was invented by Indians. It's a television scheme, I don't want to suggest that somehow all of science was developed in this period. The point is, this is a period forgotten in history that forms a continuum from the ancient Greeks and Persians, and even before that, the Egyptians and Babylonians, through carrying scholarship on before the awakening in Europe. Nor was it just a place, a repository of texts. They translated works of the ancient Greeks into Arabic, kept them, and then when Europe was ready to receive them again, they dusted them off and handed them back to be translated into Latin. This was a period of real, genuine, original scholarship. So this is a lovely map of the round city of Baghdad. It was founded in 762 AD. It was the new capital, and under the Islamic Empire was ruled at that time by the Abbasid dynasty, and Baghdad was their new capital that they built. To put it into context, there's the round city, slightly smaller area than the US Green Zone, which is probably now, I think, probably the world's largest embassy. I was born on the eastern side of the Tigris River, not a stone's throw away from the Green Zone. Baghdad has been a city that has sort of risen and fallen over many centuries and many times. But during the 9th and 10th century, it was the most important city in the world. Although there's debate among historians as to how large the largest cities in China were, many historians argue that Baghdad was the first city with a population of over 1 million. so far bigger than Constantinople or Athens or Rome, even at their height. Well, the most famous caliph of the Abbasid dynasty is probably Harun al-Rashid. So this is a painting, 19th century painting of Harun al-Rashid receiving King Charlemagne, visiting him, the two great powers of that time in the early 9th century. And apparently King Charlemagne, the stories write that he was overwhelmed by the opulence and grandeur of Baghdad and just how civilized it was. Harun al-Rashid is famous because he appears as a regular character in the 1001 Nights, the Arabian Nights. But when it comes to science, in fact, it was his son, Caliph al-Ma'mun, who was most famous for his patronage and support of science and scholarship. And it was under his rule that it believed that this house of wisdom was built, Beit al-Hikmah in Arabic. Historians argue, some historians suggest that it wasn't much more than a translation house or a library, or indeed whether it was already in existence before Ma'mun's time. But actually, you see, the problem is there's no archaeological evidence or remains of this academy, because Baghdad was a city built with sort of sun-dried mud bricks, not stone and marble like Rome or Athens. And so buildings were basically decayed away, and there's not much today left of the Abbasid period. Nevertheless, the House of Wisdom became a symbol of scholarship and learning equal to the School of Athens in Alexandria. And it was a place where many scholars gravitated. That was the place to be. So maybe today people want to come to Cambridge. This is the place to be. I say that when I go to Oxford, I say that. Okay? Or indeed some of the big American universities. But at that time, Baghdad was, so if you wanted patronage, if you wanted to be amongst other great thinkers, whether they were theologians or poets or musicians or mathematicians or astronomers, Baghdad was the place to be. And the House of Wisdom became a central draw for many of these scholars. So I want to say give a few stories about some of the scholars who lived in that period, and in particular those who made a contribution to what we would today call physics. Numbers, first of all, it's known that with the numbers, the numerals that we use, we call Arabic numerals, but in fact they're originally from India, Hindu numerals, and you can see the way they have developed as the numbers that we would recognize today. Among the decimal system, of course, is 0. And very often people mistakenly say, oh yes, it was the Arabs who gave us 0. Well, in a sense they did, they passed it on. But again, 0 came as a package with the other decimal systems, the numbers 1 to 9 from India. Indeed, who invented 0 is an interesting topic, because you have to qualify what you mean by that. Do you mean who came up with the symbol 0? Well, that was the Babylonians, just before the Mayans, something about 300 BC, who really developed and wrote about the concept of 0 as nothingness, as the void, as emptiness. Well, that was Aristotle, one of the greatest thinkers of all time. Who used 0 as a number, a number halfway between +1 and -1? Well, that was the Indians. I'm not quite sure exactly when, around about the 4th, 5th century, most likely, AD. But nevertheless, the number system is called Hindu-Arabic numerals. There's a good reason why the Arabic part of that name is still used. I don't expect you to read this. This is a text from the 10th century by an Arab scholar by the name of Al-Khalili, the Euclidean. He earned his living by translating and commenting on Euclid's great work, the Elements. Euclidean geometry that we still all learn at school today. Parallel lines and triangles and circles and triangles and circles. That was all in Euclid's geometry. It was a synthesis of the work of mathematics and mostly geometry of the ancient Greeks. Well, in this text, he's not commenting on geometry. What it gives us is the very first use of the decimal place. Zooming in, so there's this number here, see what PowerPoint can do. You see, so this number is 179685, and there's a dash over the 9. What that number is, here, for you to recognise, 179 plus 685, it seems rather sort of random looking number. Where does it come from? He was doing an exercise in arithmetic to show the usefulness of decimals over fractions. So this is what he was doing. He said if you take a number and add to it its tenth, and then take that number and add to it its tenth, and so on, several times. So for those who are mathematically inclined in the audience, that is that number, whatever it is, times 11 tenths cubed. The number he chose, sure why, was 135. But in any case, what he was trying to explain is if you wanted to write that number in terms of fractions, it's quite cumbersome and awkward, and it's much more convenient and simple to write as a decimal. So this is the first known example of the use of the decimal place, the decimal point. And so since the decimal system is part of the number system we use today, we talk about Arabic Hindu numerals. This is the front page of a book by a Persian mathematician by the name of Al-Khalili. He worked in the House of Wisdom. He is regarded as one of the greatest mathematicians of all time. Why? Because he is regarded as the father of algebra. And I will explain why. First of all, the word algebra, you may know, the word algebra comes from the Arabic, al-jabr, which was the title of his book, Kitab al-Jabr, the book of completion. That's much longer title, but al-Jabr became the word that we use for algebra. Of course, you don't accredit someone with being the father of a field just because that field is named after the title of their book. But he was the first person to really do algebra the way we understand it today. Of course, many ancient mathematicians were doing what we might think is algebra. Even the Babylonians knew how to solve what are called quadratic equations. Okay, so they would say if you take a number, add to it its reciprocal, 1 over it, and if that equals some given number, here's what you do to work out the number. Okay, so what they were doing is this was an example of what's called a quadratic equation, an equation that involves the unknown, the x, squared. We all learn at school. You all will have learned at school, even if you've forgotten it now, right? The solution to a quadratic equation, minus b plus minus the square root of b squared minus 4ac over 2a, right? Anyway, the Babylonians, even long before the Greeks, so we're talking about the 2nd millennium BC, knew that formula and were able to use it. But they weren't doing algebra. They were solving specific problems for specific examples. So if you have the equation, this is the formula. They weren't giving the general recipe, the rules needed to solve general types of equations. Similarly, a Greek mathematician, Diophantus, wrote a book on what was essentially what's called number theory today. That's the area of mathematics. And he wrote about a class of equations which are now known as Diophantine equations. Well, maybe I won't go too much detail about them, but there was also an Indian mathematician, Brahmagupta, who also liked to solve these sorts of equations. And they had a general form which looks like what I've explained just now, the quadratic equation. But look, there were two. The little n is regarded as a number that you assume when you solve a particular problem, you know what that is. And you want to find what x and y are. Well, of course, you can have, for a given x, there'll be a given y, for a different x, there'll be another y. So these are quite awkward equations to solve. The Babylonians wouldn't have been able to do this. Brahmagupta, the Indian mathematician, posed a challenge. He said, can you find a solution? What possible values of x and y can you have if a was 92? I'm not asking you to do that. In fact, Brahmagupta suggested that anyone who could solve this problem within a year could then qualify himself as a real mathematician. Today, it's easy. We have computers to do that job, churning through. Okay? Right, so let me just finish that bit about algebra. So, people were doing what we might regard as algebra. What did this Persian mathematician, Al-Khalili, do that was different? Well, one thing that he did that was different that's very, very sort of fascinating is that he wrote essentially a popularized book on mathematics. A book that was accessible to many people. In it, he explained how to solve problems to do with inheritance, with tax laws, with agriculture and division of land, all sorts of practical issues that would have been needed by many people across a bustling society. What's fascinating is this is a book on algebra without a single equation. The whole book was written in prose. So he'll say, you take the unknown, the thing, he called it, the thing, in Arabic it was shape. You take the shape and you multiply it by itself, then you add to it 3 times the shape, and so on. And without an equation, he was able to develop a whole field. So what was so fascinating or original about his work? He was the first person to say that the x, the unknown quantity, was a real entity in itself. It wasn't a symbol hiding behind which was a specific answer. It was a thing in itself, and you follow a recipe, a set of rules to reach an answer. And he gave the general, the steps for solving a general set of equations. What today we would call an algorithm. An algorithm comes from Al-Khalili's Latinized name, algorithmus. So mathematicians today, and it took me a while for the penny to drop. I remember talking to the mathematician from Warwick, Ian Stewart, who's written a lot of popular books on mathematics, and he explained this distinction, why Al-Khalili really deserves to be the father of algebra. Okay, my next character is a man who many in the West don't know, and that's just because he wasn't lucky enough, I guess, to have a lot of his work translated into Latin. Because there was a second translation movement much later than the one that took lots of Greek texts and had them translated into Arabic. Many Europeans, when they were aware of the scholarship going on in the Islamic Empire, travelled there, learnt Arabic, and translated these texts into Latin. Some of them were originally Greek, so they were translated the works by Aristotle and Plato, and Euclid and Ptolemy, from the Arabic into the Latin, because very often those were the only versions of those texts that were still extant. But the translations took place in cities like Cordoba and Granada and Toledo in Spain, Andalusia, because that was essentially the gateway to Europe. And someone like this guy here, Al-Biruni, Persian polymath, who travelled extensively around Central Asia, wasn't known in Andalusia. I regard him as the Da Vinci of the medieval world. There isn't a discipline that he didn't have a hand in helping to develop. From history to anthropology to trigonometry to astronomy, the list goes on. It's a wonderful debate that took place between Biruni and a contemporary of his, the real superstar of the medieval world, Avicenna. Avicenna is the Latinized name, his real name is Ibn Sina. And they both lived 10th, 11th century. And they were the giants of that period. And they had these debates, essentially about physics. The debates remind me of a more recent debate between two giants in early 20th century physics, Albert Einstein and Niels Bohr, arguing about the meaning of quantum mechanics. These guys were arguing about things like, so Biruni would write to Avicenna and say, so why does ice float? It's a solid, shouldn't solids be more dense than liquids? And Avicenna wrote back saying, oh, that's because ice has tiny holes in it, and that makes it lighter. I'm not sure about that. Debating about how does the sun's light and heat reach the earth? Is it a real substance? Why doesn't it heat up? Why if you hold something, an object gets warmer but the air above it isn't at the same temperature? These are sorts of debates that we just see the early shoots of the modern scientific method in the way they discuss and argue about potential theories and trying to think of experiments that they could do to test this. No one else had done this before, other than probably Archimedes. Archimedes was the great physicist of the ancient world. What Biruni did that was fascinating and that has become quite famous was that he measured the circumference of the Earth more accurately than the Greeks had done. Now, the Greeks knew the world was round. There's this fallacy that we thought the world was flat until Christopher Columbus went all the way around. The Greeks knew that the Earth was round. They measured the circumference. But what they did was something very crude. They would measure the angle of inclination of the sun and then walk, counting footsteps, until the angle changed by 1 degree. And they said, well, to change by 360 degrees, I have to multiply the distance I've travelled by 360, and that gives me the full circumference. Actually, not a bad method, and they came very close. Biruni said, that's not a very reliable way, counting footsteps, pacing across the desert to try and measure distances. Here's a much more elegant technique. What he does is measure the height of a mountain. He uses some technique that modern surveyors would recognise in terms of looking at angles and triangles, and so he had a device where he could measure. I won't go through the details, but essentially he used trigonometry, he used the idea of similar triangles, and could work out the height, Fe, of a mountain from a flat plane, looking at it and measuring different angles of inclination to the top of the mountain. Then, having worked out the height of a mountain, and he did this somewhere in Pakistan when he was on his travels, he would then go to the top of the mountain and measure the angle of inclination to the horizon. So it had to be a mountain overlooking the sea or a flat plain so he could see the horizon clearly. And the angle of the horizon as an inclination from the horizontal. So he could measure the horizontal line because he would have a plumb line, and he'd have some elaborate astrolabe, a device that could measure angles, and he could measure this angle, this drop, a bit like half a degree. That's the angle phi, and if you know a bit of geometry, this would be something that Euclid would have taught us. That angle phi is the same as the one down there inside of that slice of the circle. So this circle is the Earth, that's his mountain on the top. He could rearrange these symbols. If he knew h, the height of the mountain, and he knew the angle phi, there's a bit of trigonometry that the cosine of phi gives us an equation, and the only thing we don't know there is big R, the radius of the Earth. So he could rearrange, manipulate this equation, and work out the radius of the Earth. He knew to multiply it by 2 pi to give the circumference. And he got that, what is roughly just under 25,000 miles, and he got to within 1% of the modern value. Of course, you know, it depends really where you measure the circumference. Around the equator, the Earth is fatter than it is around the poles. But nevertheless, it's not how close he got, it's the ingenuity of his method. He helped develop a lot of trigonometry. Trigonometry was very crude during this period, and people like Biruni helped develop it way beyond anything that the Greeks or Indian astronomers knew about. Just as an aside, do I have this? I mean, do people want to go at 6? Should we be rushing? You haven't got anywhere to go to. Good. Okay. Because this is quite fascinating. I mean, don't worry if you're not so interested in trigonometry, but the origin of the word sine is nice because it comes from the Indian. There was an English scholar called Robert of Chester in the 12th century. He was the person where we inherit the word sign from. It comes from Hindu. So etymologically, we begin with the Sanskrit, and there's a word, ja'arda, which means half the bowstring. So imagine this thick line here is the shape of a bow, and the vertical chord is the string of the bow. So half the bowstring is that side of that right-angled triangle. Now, this circle of unit radius, then actually that side gives you the sine of the angle A. Okay? So the sine of an angle, ja'arda, was abbreviated to jiva. Jiva was then translated when the Arabs learnt about this definition. They renamed it because there's no V letter in Arabic. So that became jiva. And of course the vowels in Arabic, if they're short vowels, they don't, you just basically write that word as the j, b. the J and B. So it became known as J, and J means, it doesn't mean pocket, it just happens to mean pocket in Arabic. Okay, so when you see that J, Robert of Chester, who learnt Arabic, thought that word was spelling out the word pocket. So he just took the Latin for pocket. It's understandable. But it's sort of fun to think that's where it came from, just from a mistaken translation. Okay. I want to talk about my favourite physicists during this period. If we think about the greatest physicists in history, Archimedes, I think, without doubt. People like Aristotle were great thinkers, but Aristotle was more of a philosopher than a physicist. If anything, he was more interested in life sciences than what we call physical science, and zoology and so on. Archimedes, however, was a physicist. Okay? He carried out experiments with lenses and famously running through the streets shouting "Eureka" because he realised that objects immersed in water raise the level of water. Span of 2,000 years until the greatest physicist of all time, Isaac Newton. I'm not arguing about the place of these two greats in history. My question is, who's the greatest physicist in that 2,000-year period? Now, there are many candidates. Notably, you might think someone like Kepler or Galileo. Yeah, but that's sort of, boring. Kepler and Galileo were very clever blokes. But this guy, Ibn al-Haytham, is an unsung hero in the history of science. He was a contemporary of Avicenna and Biruni, but he didn't travel around in Asia. He lived in the Middle East. He was born in Basra in southern Iraq. And he's a wonderful character. He started off working in a job which essentially was a sort of administrative civil service job in Basra, which he found very boring. Now, famously, Einstein worked as a patents clerk in Switzerland. He found that very boring, but he found enough time to come up with relativity theory and publish so many papers at the turn of the 20th century. Ibn Haytham adopted a different attitude. He wanted to read Ptolemy's Almagest, the book of astronomy. He wanted to read Euclid's Elements. He didn't have time for all this boring administrative work. So what he does, he feigns madness and gets sacked. And it's not known whether he walks around, drooling or whatever, but the fact is he's allowed then to go off and do what he wants and pursue scholarship. He then finds out there's the new dynasty in Egypt, the Fatimid dynasty, who have just created their new capital, Cairo, it's become sort of a wonderful place for scholars to go to. He writes to the Caliph in Cairo and says, "I've realised there's a way to solve your problem regulating the flooding of the Nile. What you need to do is to build a dam across the Nile, somewhere where modern day Aswan is actually." And so he says, and I can design it for you. So the Caliph invites him over to Egypt, and he goes down to see the site where he thinks is most appropriate, and realises he's bitten off more than he can chew, and this is not an engineering project that he can solve. So because he's worried now, the Caliph's not going to be too pleased that he's going to let him down. What does he do? He feigns madness and gets away with having his head chopped off. But he's put under house arrest in Cairo, near the Al-Azhar Mosque, for 10 years until the Caliph dies. And during those 10 years, he publishes his greatest works. And he writes a book on optics that is in every bit as important as Newton's book on optics 7 centuries later. His book, translated into Latin, is called De Perspectiva. In it, he was the first person to explain how vision works, how we see things. The ancient Greeks, clever though they were, couldn't decide whether when you see an object, it's because light from the object shines into your eyes, or whether it's light from your eyes shines out at the object. So people like Plato and Aristotle stood on different sides here. They couldn't agree. Well, Ibn Haytham was the first person to explain what it is, and he uses what we would now call ray diagrams, straight lines. He said light travels in a straight line. He used lines with arrows and showed that how light bounces off objects, angles of incidence and reflection into the eye. He also writes about refraction. He also writes about perspective and depth. In fact, his book, when it was translated into Latin, De Perspectiva, became very influential among Renaissance artists, in Florence in particular. And so it was known, his work was known among European scholars during the Renaissance. He also famously, there's a problem in mathematics called Al-Hazin's problem. Al-Hazin is his Latinized name, but it's his Latinized first name, Al-Hasan. So it's not Ibn al-Haytham was Latinized, it was his first name. So he's known in the West as Al-Hazin. You may have heard of that name, Al-Hazin, rather than Ibn al-Haytham. And the problem he sets and solves geometrically is, you know, we know about angles of incident reflection. When you play billiards or snooker or pool, you know that to bounce the ball off the cushion is going to bounce off a reflected angle. Anyway, you know about that. But if the wall of the cushion is round, then it becomes much more difficult, and you have to hit precisely the right point in order to bounce, say, a light beam into a particular direction. Finding that point is a very difficult problem in mathematics, and it requires solving what's called a quartic equation, an equation not involving x squared, but involving x to the power 4. Well, the way he solves it is using a method called conical sections, where you slice through cones at different angles to produce different two-dimensional shapes, circles and ellipses and so on. And that geometric technique he applied to solve this problem. And you know, no one had been able to do this before. Many other mathematicians afterwards refined the technique. In particular, one mathematician, Persian mathematician, I'm sure you'll have heard of him, Al-Khalili, better known as a poet. Well, he was a better mathematician than he was a poet. He was one of the greatest mathematicians, and he was no mean poet. I'm not studying poetry, but he was a wonderful mathematician. So he advanced the geometric techniques of Ibn al-Haytham. He advanced the algebra of Khwarizmi as well. Okay, while I'm on talking about light and optics and refraction, there's an even lesser known scholar by the name of Ibn Sahal. A diagram that was discovered recently by historians of science has only recently been understood, and it's to do with working out a law that we all learn about at school to do with refraction, called Snell's law. If you have a light beam, say travelling from air and down into surface like water, we know the idea that a spoon looks bent in a glass of water because light is refracted, because light slows down when it goes from air to water, different media. And so the Greeks knew about this, but the way they worked out these angles was not to say that the ratio, what they thought was the ratio of the angles was a constant. And that isn't quite right. What turns out to be correct is it's the ratio of the sine of the angles. The sine of the angle of incidence divided by the sine of the angle of refraction is a number that is to do with the two media. To do with what's called the refractive index of air and water. Well, Ibn Sahal was the first person to correct the Greeks' version. He said, when you look at the ratio of the angles, essentially what you're doing is dividing the two curves, the two bits of the arcs of the circle, the top thick line and the bottom line. What you should really do is not divide those curved lines, but divide the straight lines. And that's essentially, that means dividing the sines of the angles. So Ibn Sahal really should be regarded as the person who came up with Snell's law 6 centuries before Snell. And science is littered with these stories where people have come up with something first, but because their work wasn't propagated or wasn't known about, they are sort of rediscovered much later. In astronomy, well, Ptolemy's book, Almagest, was the greatest text on astronomy in ancient times, and he had a geocentric model of the universe. So Ptolemy and all the Greeks believed that the Earth was at the centre of the universe, and all the other planets orbited around it. And sometimes they would do rather complicated things, so they knew it wasn't as simple as everything going around in a circle, but they wanted circles. They wanted everything to be in terms of circles. Aristotle had this great influence, everything has to be very beautiful. So they had circles orbiting around circles, and it all got very cumbersome, but Ptolemy was able to develop a wonderful theory that fitted this geocentric model of the universe. And even that wasn't accurate enough when we're talking about the orbits of Mercury around, or some of the other planets around the Earth. So that wasn't enough, and they had to shift the Earth away from the centre. In fact, that diagram is wrong. The point called the equins is in fact not the centre of the circle. Believe me, if that's cumbersome, it's the actual, if I draw that correctly, that would be even more awkward. The fact is, the Greeks thought we had this special position in the universe. The Earth was at the centre. And famously, we know that Copernicus was the man who gave us the heliocentric model of the universe, that replacing the Earth with the Sun at the centre. Well, I'm not suggesting that the astronomers of medieval Islam arrived at the heliocentric model first. In fact, a number of people had proposed Copernicus's model, even during ancient Greek times. Famously, of course, this is Copernicus's diagram from his great book, De Revolutionibus, which has the sun, Sol at the centre, and the Earth is just another planet with the moon, so Terra, with the moon orbiting around the Earth. And we do tend to credit Copernicus with being the father of modern astronomy, indeed the father of modern science itself. Just like the ancient Greeks, just like all the Arabic astronomers, Copernicus did all his astronomy without a telescope. Because Galileo came after astronomy. Galileo was the first person to stick a telescope up, pointed towards the sky, and look at the heavenly bodies in more detail. And it was Galileo who confirmed that the Earth isn't at the centre of the universe, that the Sun is at the centre of what was then regarded as the whole universe. Well, so what did the astronomers of medieval Islam have to say about astronomy? Well, the question is this: was Copernicus the first person to propose the heliocentric model? And in fact, he wasn't. There was a Greek astronomer by the name of Aristarchus, 3rd century BC, who said it's not the Earth that goes, the sun that goes around the Earth, it's the Earth that goes around the sun. Not only did people not believe him, but they slapped him down, they ridiculed him. So the famous quote by Archimedes, he said, "You know that most astronomers designate by the word cosmos the sphere whose centre coincides with the centre of the Earth." Obviously, that's the sensible thing. Aristarchus, that fool, I'm putting words in Archimedes' mouth here, assumes that the fixed stars and the sun remain stationary while the Earth moves around the sun through the circumference of a circle. How ridiculous! Well, that's exactly what we now know to be the case. So Aristarchus, like Copernicus, was a revolutionary that people didn't believe at the time. Indian astronomers had also proposed a heliocentric model and were slapped down. And there was an Arab astronomer by the name of Al-Sijzi who also proposed a heliocentric model. Interestingly, Al-Biruni, my Da Vinci of the medieval world, supported Al-Sijzi's heliocentric model. Not wholeheartedly, but he said, well, the Earth goes around the sun goes around the Earth, surely it depends on your point of view. Oh, that's relativity! Just like these early astronomers, Copernicus was, of course, he was courageous in going against the perceived wisdom, but like them, he was just guessing. What did he do there that was different? Well, he did turn what everyone else had really regarded as just a philosophical idea into a proper, fully predictive mathematical theory. A theory that was then confirmed by other astronomers after him, like Kepler, Galileo, and Newton. What's interesting, though, is Copernicus used mathematical techniques that he had inherited from the Islamic world. So this is a comparison of two diagrams. This is now quite well known in the history of science. So this is from Copernicus's text, And this is another diagram from a book by a Persian astronomer by the name of Tusi. What's interesting, it's quite difficult to tell from these diagrams, because all astronomers are drawing circles within circles. I'm not suggesting that he plagiarized because the diagrams look the same, but what is the same is the use of the letters, because the Latin letters that he used follow exactly the translation of the Arabic alphabet, alif, ba, ta, ta, jim. So that order of letters labeled in that diagram is used in that one. And there are in this text, there are other examples of the mathematical techniques that Copernicus used, suggesting he would have had at his disposal Latin translations of texts from medieval astronomers in the East. And this is something that's only really coming to light. But really the father of modern astronomy I would regard as Galileo, because Galileo was the first person to use a telescope. And this is a wonderful picture here from the frontispiece of a text in the 17th century by an astronomer by the name of Babbage, who studied the moon. And on the front cover, he has the two men that he regards as the giants of astronomy. So he has Galileo on the right with his telescope, and Ibn al-Haytham on the left with his geometry diagrams in his hand. So, and he sets them up as the experimentalist and the theorist working together. So back then it certainly was known how much credit should be given to some of these medieval physicists and astronomers. Ibn al-Haytham, I've almost finished now. Ibn al-Haytham is also regarded by many historians now as one of the fathers of the scientific method. Now, it's always very difficult to say, that what we call science began with this person. But we do tend to think that it began with people like Bacon and Descartes, much later. Well, here's a text from Ibn al-Haytham. He says, "We should distinguish the properties of particulars and gather by induction what pertains to the eye to be uniform, unchanging, manifest and not subject to doubt. After which we should ascend in our inquiry and reasoning gradually and orderly, criticizing premises and exercising caution in regard to conclusions. Our aim in all that we make subject to inspection and review, being to employ justice, not to follow prejudice, and to take care in all that we judge and criticize, that we seek the truth and not be swayed by opinion." That's sort of the scientific method. That's how we do science today. And Ibn al-Haytham was one of the first people to come up with an idea, a theory to do with optics and vision and the way light behaves, and then to set up and design an experiment. He did a lot of work with the pinhole camera obscura, that was invented in China. And he would design experiments, and then he would write up his experimental setup and explain what he did, explain his measurements meticulously, so that others after him could repeat those experiments. And if an experiment disproved a particular hypothesis or idea he had, he knew that that must be wrong. So that is, for me, the early sort of scientific method. I just want us to end by saying, maybe we want to ask a question at the end, but essentially, we think of the golden age of Arabic science, if we know anything about it, as having gone into decline and disappeared by the 12th, 13th century. And that's not the case. It certainly went into decline gradually. Fragmentation of the empire, scholarship was no longer supported and rewarded with patronage, as different dynasties and sultanates were more interested in fighting with each other than with scholarship. And it's just the natural course of events. Civilizations rise and fall. No one asked what happened, what went wrong with Greek science, why did that suddenly end? But in fact, it ended much later than many people think. So even up to the 15th century, there were great scholars in mathematics and medicine and astronomy. So a mathematician by the name of Al-Khalili worked in Samarkand in Central Asia. And he calculated famous pi to 16 decimal places. He gave us the cosine rule. And in fact, the cosine rule, which we learn at school now, in French, it's attributed to Al-Khalili. So they remember that he was the first person to come up with the cosine rule. In calculating pi, he said beforehand, I'm going to calculate pi and I want it to this level of accuracy. So I'm going to develop this geometric technique, something that had originally been developed by Archimedes, but he did it much more accuracy. So there was a lot of scholarship that carried on much later than the period when we think Europe had taken over. I want to end then with this quote by a historian who says, when it comes to understanding our world through reason and experimentation, the Greeks systemized, generalized, and theorized, but the patient ways of investigation, the accumulation of positive knowledge, the minute methods of science, detailed and prolonged observation and experimental inquiry, were altogether alien to the Greeks' temperament. What we call science arose in Europe as a result of a new spirit of inquiry, of the methods of experiment, observation and measurement, of the development of mathematics in a form unknown to the Greeks. That spirit and those methods were introduced into the European world by the Arabs. Well, when we say Arabs here, that's incorrect. It's in the Arabic language. As I say, many of these great scholars were not Arabs, they were Persians, and they come from many other races. So it's a wonderful period in history where I found it very inspiring to see these nuggets of these great scholars that we know very little about, and how they fit into the story of the development of science. Science doesn't, civilizations rise and fall, but science is a continuum. It's the body of knowledge is a baton that's handed on from one civilization, from one culture to the next, who assimilate and build on it and then hand it on. It carries on in steps like that. Every now and again you have great geniuses who make big leaps forward, but behind those big leaps forward are these other giants on whose shoulders Newton said he stood. And some of those giants came from the East, from the medieval Islamic world.
So Jim is very happy to answer a few questions.
And I won't take it as rudeness to those of you who need to leave, because I know I'm getting on what I'm happy to answer. Was the camera obscura invented in China? Yes, I think a lot of texts I've found have suggested that camera obscura was invented in the Islamic world, but we know very little about Chinese science, mathematics, and this is one of the things that can be traced back. There are very few scholars who studied what was known in China. So when I talked about the decimal place, it is possible that Chinese had already developed the decimal system and decimal place at the same time or even before. But the Chinese didn't assimilate or mix as much as, say, the Indians did. So Indian science and learning was influenced very much by the Greeks through Alexander the Great, and a lot of that was then translated into Arabic. Not so much is known about what we inherited from China. The camera obscura, I believe, is one of them. Paper making is a very famous example of another important reason why the Islamic world was able to advance so quickly, because they inherited paper-making techniques from China, and that allowed them to produce books more cheaply than papyrus and parchment. But I think, as far as I'm aware, I don't know too much details about exactly when, but the camera obscura was a concept that was written about by Chinese scholars that passed westward through India to the Arab world. Okay. Yes. Yes, and in fact, the text of those debates has now been published as a book.
What was the question?
Sorry, the question. Sorry, I do apologise. The debate on physics between Biruni and Avicenna on the nature of sunlight and the nature of why ice floats and so on. The whole correspondence between them has now been studied by scholars and has been published as a book that I can't remember. I don't know, are there any historians of science in the audience who will know? Okay, well, it is available. I guess if you search online, that'll lead you to the text, but there is a book available that I've only recently got hold of and I haven't had a chance to read carefully, in English.
Put it as a hashtag on the CSF.
Okay, I shall do that. I shall tweet the name of the book available. Did any of these scholars come into conflict with the powers that be? Very interesting question. Yes, they did. There's a whole chain of philosophers from a man called Al-Khalili, who was an Arab, to a Turkish philosopher called Farabi, Avicenna, Averroes in Andalusia, were all regarded as heretics because they were deemed to be too Aristotelian in their thinking. What they did was assimilate Aristotelian Greek philosophy with Islamic theology. And by about the 10th or 11th century, there was a move towards more orthodox, conservative Islam, where that was deemed to be a bad thing. There was one of the most famous theologians of the Islamic world, Al-Ghazali, wrote a famous book criticizing Avicenna. And the book's title was The Incoherence of the Philosophers. He didn't like, he just said it was nonsense. Averroes comes later and criticizes Al-Ghazali's book, and his title is The Incoherence of the Incoherence. And that is a very famous and influential text. And in fact, people like Avicenna and Averroes, despite coming under attack from theologians in the Islamic world, were regarded as the people who were able to assimilate Greek philosophy with Islamic theology. So Maimonides, the great Jewish theologian, studied the work of Averroes and Avicenna and incorporated Aristotelian philosophy into Judaism. And then Thomas Aquinas does the same thing by studying their work assimilated into Christianity. So yes, but they were criticized, and in a sense, after Al-Ghazali, philosophers become a bit more careful about their pronouncements and what they say. But back in the early days, in the 9th and 10th century, there was a wonderful openness and freedom where there was no conflict between science and religion. In fact, it was their religious duty to go out and do science. Quite in contrast to a lot of attitudes towards science in the Islamic world regrettably today, which sees science as an atheist Western construct that is threatening. So back then, 1,000 years ago, there was no issue. And it's interesting to know, just to ask how far the Islamic world today needs to progress to regain that spirit of rational inquiry that they had in freedom of thought.
Any other questions? Yes,
Can you comment on the characteristics of society which promotes open inquiry, such as the time in the Arab world? We now see perhaps in the West with the rise of Christian right.
Yes, so the characteristics of society during the Abbasid period was very open and tolerant. They valued learning. A lot of it, this was driven by the new religion, by Islam itself, which says, you go and seek knowledge wherever it may be, even if you have to go as far as China. Astronomy developed because they needed to know when to pray, they needed to know when to fast during Ramadan, they needed to know where to face to point towards Mecca. That needed developing geometry and spherical geometry and astronomy. Medicine and issues of health developed because of the Islamic teaching of cleanliness. So these are lessons that, while Europe was mired in filth and dirt, the Islamic world was very, very different. And so it was a period of tolerance and openness. And you see a lot of, in Baghdad, there were a lot of famous scholars, great mathematicians who worked in the House of Wisdom who were Christians, great philosophers who were Jewish. A lot of the physicians of Baghdad were Christian. And a lot of it was inherited from the Persians. The Persians had this one... Islam developed out of Arabia, out of a tribal society that didn't have this great historical heritage and culture. But Baghdad was influenced very strongly by Persia, and the Persians really were into learning, and they valued it very highly. So that was the spirit that was around at that that time. One of tolerance.
Yes, question there.
Yes. I've looked around to see, where were the great women scholars of that period. The fact is, not much is known. There was a woman who was known as Al-Khalili. She built astrolabes, and she's known to have made a number of astronomical measurements, and she worked alongside the men. But not much else is known. But then, how many Greek philosophers who were women can we name? I think it's not. I don't think it's a reflection on the intolerance of the religion of the time. It's just a reflection on many cultures, including today, unfortunately. Yes.
You mentioned that Al-Khalili was what you call the Da Vinci of medieval work.
Yes.
Did he do anything in the so-called creative arts, music?
Biruni, I call him the Da Vinci, so let's see how close the parallels are. Did he do anything in the creative arts and music and so on? No. I mean, he wrote a lot of work in the humanities. So he wrote a very famous text on the history of civilization. He wrote a book on the geography of India, and he's regarded as writing the first text on geology and the environment. But when it comes to creative arts of music and so on, he didn't do much. I should say that back then, certainly back in the 8th century, music was deemed as one of the branches of mathematics. So mathematics was numbers, arithmetic, geometry, and music, and then algebra joined them. So some of the great philosophers were also developing the theory of music. So Al-Khalili, the great philosopher like that, certainly wrote a lot of text on music. But Biruni, no, that's something Da Vinci has on him. But he was good at drawing as well.
So I think that's a good point too. Okay, there's one person waving their arm.
Okay, right.
There's a musician called Ziria. I think he was in the 12th century. Does that have anything to do with science?
What was the name?
Ziria.
Yes. Ziria. He travelled from the Middle East and settled in Andalusia. Yes, that's translated as the blackbird. I think that's his name. Yes, yeah. He's fantastically colourful character. I also write about him in the book. He showed the Andalusians, the benefits of brushing their teeth, combing their hair. He was into fashion. He was the Gokwan of Andalusia. He was a fantastic character. I don't know how much science he knew, but he was lauded by everyone wanted him round for dinner.
I think that's probably a good point. Okay, so I think we should thank Al-Khalili again for a fascinating discussion.